Okay, so we would like to introduce triple integrals in cylindrical coordinates, so switching from Cartesian to cylindrical coordinates. The first step in this process is to express our domain in cylindrical coordinates. So I will put question marks for the limits that have to be worked out. And the cylindrical coordinates are dr, d theta, dz. It's not a given that the integration has to take place in this order, but we put this tentatively. And we recall that the transition equations that we should remember is that x is r cosine theta, y is r sine theta, z is z. And also it's useful to remember that x squared plus y squared is equal to r squared. Now, let's also recall how the cylindrical coordinates work. If you have a point, then what you do is you project it onto the xy plane, and you get the polar coordinates of the projection. So you have the angle theta and the distance from the origin. And then you also attach to them the angle z. So once we express our domain in polar coordinates, then we express our function using polar coordinates. So that's the next step. And sorry about this. And finally, we multiply by the Jacobian, which is r. So this is the Jacobian for cylindrical coordinates. This is all the preparation that one should do. And let's work out our example now. So in our example, we have a part of a cylinder that has radius 2. Okay, it's parallel. The cylinder is parallel to the z-axis, and it goes from z equals 0 to z equals 3. So if we want to describe our domain in terms of cylindrical coordinates, then r goes from 0 to 2. Again, we see this from this description. Think of 4 as 2 squared. Theta is going all around. Again, it's never a problem to actually write from 0 to 2 pi inclusive. One might think that points that have angle 0 also have angle 2 pi, so some points may be described twice, but those points that are repeated correspond to a part of the region that has volume 0. And finally, z is between 0 and 3. Now we have everything that we need. So we will have the triple integral. We can put, since all the endpoints are constant, we can put them in any order we like. D theta and 0 to 3 dz. And we'll do our integrand is z, remains z, because again, z is a common coordinate between the set of cylindrical coordinates and the set of Cartesian coordinates. And finally, the last step is that we should multiply by the Jacobian. Now we're ready to carry out the integration. So we will have the integral from 0 to 3, integral from 0 to 2 pi. The antiderivative of z times r with respect to r is z times r squared over 2 from r equals 0 to r equals 2, and then d theta d z. And this will give us the integral from 0 to 3, integral from 0 to 2 pi of 2z d theta and then dz. The antiderivative here is just 2 theta to zeta theta, because this function to zeta is 2z is constant with respect to theta. So that will go from theta equals 0 to theta equals 2 pi, and then dz here, which will give us the integral from 0 to 3, and then 4 pi z dz. Finally, we have a sort of interesting integration. So this will be 2 pi z squared from 0 to 3. And this will give us 2 pi times 9, which is 18 pi. And that's our integral. Please note that this integral doesn't describe the volume of this region. If we wanted to describe it, it would to interpret it, then it would actually represent the volume of a four-dimensional region that lives in 4 dimensions that obviously cannot be visualized. This is just the domain of definition of the function. And that's all. Thanks for watching.